Good afternoon, everybody. Welcome to Balluff's WebEx. This is the fourth WebEx in our continuing WebEx presentations. This is going to be on stamping. This is the applications portion of the stamping. I'm Kevin Sargison. I'm here with Jason Diaz. We're going to be presenting the WebEx today. So we'll get started. So our topic again is stamp out errors. This is the applications portion of stamping. We're going to begin with a quick review of the top 10 questions to justify an in-die sensor program. Why we're going to start here is just recently we uncovered a financial report from last year from one of our large Tier 1 automotive customers, and they highlighted 6 of these 10 questions that are listed here. So if these are important enough to be included in a company's financial statement, they're important enough questions for you to ask when you're talking to the tool room or the tool room supervisor or the production supervisor regarding stamping. So we'll just start here with a quick review. What is the cost of die repair? What is the cost of die crashes? What is the cost of press downtime? What are the costs associated with secondary operations? What is the cost of overtime labor? What is the cost of rework and sorting? What is the cost of express shipment of finished goods? What is the cost of firefighting? What are the costs of scheduled alterations? What is the cost of lost consumer goodwill? There's one common component in all 10 of these questions, and that is the word cost. So try to keep those 10 questions in mind as we go through the applications. It'll help you. First thing we're going to look at is cam return monitoring using inductive proximity switches. So you can see the inductive prox switch at the bottom left-hand corner of your screen. So here we're using it to detect a cam returning to the home position. Slug Out Detection. Here we're using 3 of Balluff's ring sensors to look for slug outs, to make sure that when the presses come down and stamp out a slug, that the slug actually falls through the bottom of the press and does not get caught where it can cause a die crash. Transfers, grippers, and shovels. Sensors are used to verify that the part or multiple places on a part were grasped and that a part did not fall out. So you can see the example of the progressive die going up and down, and the transfer picking up the part, that's in the left-hand corner, picking up the part and moving it through the cycle of the press. So depending on what type of gripper is used, we may want to utilize inductive sensors, photoelectric sensors, or some type of magnetic field sensor to tell that we have actually gripped the part and transferred it to the next set of fingers. So here we look at our BWL sensor as our transfer shovel sensor. This is a through beam sensor that is built to be very robust and to have a high excess gain to help with the contaminants found in sensing applications. That would be cutting fluids and lubricants. So as you see, no adjustments are necessary. There's no potentiometers on this photoelectric sensor that would allow ingress of any liquid. It is a through beam, so it's highly dependable, and we basically have to have the beam broken in order to sense the part. So you can see in the application example that once the beam is broken with a part, then you'd get an output indicating that you have something in the transfer shovel. Here's another example of what the transfer shovel would look like with the integrated BWL sensor. Here's another type of sensor, BWL used in a jaw type transfer. So there you can see the top and bottom of the jaw firmly grasping the metal blank and the sensor detecting when the blank is in place. Here's a parallel gripper using an analog feedback sensor to measure the travel of the jaw. You'll see the analog prox with the circle around it. You'll also see a tapered metal target. So that tapered metal target, when that slides in and out with the jaw opening and closing, it would provide an analog signal through the prox to the control system to tell them how far the jaw is opened or closed. This will not only tell us that we have a part in place, but it can also be used to tell us what type of part we had in place. So if the press was doing multiple operations, we could actually gauge what part we had in place by the feedback from the analog sensor. Photoelectric sensors in metal forming. Where would we use photoelectric sensors in die and press applications? So what it's showing you here is some common sense with regards to using photoelectric sensors and stamping is required. We typically don't want to use a photoelectric sensor in an application where we have a lot of contamination in a stamping press. So if we have large amounts of lubricant or coolant, we typically don't want to use a photoelectric, and if we do use one, we want to make sure that it's a through beam sensor. Here we're looking at a single-sided, likely a diffuse or a background suppression sensor in a highly contaminated environment. In this application, we're looking at using a photoelectric sensor to detect parts falling out of the die or part out. Why is this important? Well, we want to make sure the part actually ejects from the die before the die comes down and stamps the next part. Because if the part doesn't eject, that's when we get into damaged tools and die crashes and costly repairs. Here's a through beam sensor doing detecting a single part falling out of the die. So you can see with the red line, this would be an infrared sensor, but the red line is used to illustrate where the beam would be. The part just breaks the beam as it passes, and if the part does not evacuate, the press would stop so that our die doesn't smash a part that is caught in the die. Here's an example of multiple part out. So you have a dual-sided press, you have two parts falling out, one on the left, one on the right, and in this case they are using a diffuse sensor to pick up the part as it falls out. Now this is a diffuse sensor that is at the end of the die, so there may not be as much lubricant or cutting fluid present. That's where you would use a diffuse sensor. And you can see that the sensor is protected with a bracket on the right-hand side of your screen to make sure that the sensor is not damaged. And it's also protected with the aluminum housing encased up inside so that parts don't hit it and that it's not getting damaged by the metal part. Here's probably the best sensor to use in any die application, a through beam, not necessarily always a through beam laser, but a through beam sensor. This is looking at the feed, so the laser is positioned to see through flanges on the part, a long or short feed, and the beam is broken, sending a signal to press control. So earlier, if you remember back to last month, we had some short feed examples using inductive sensors where we were looking for a hole. And if we sensed the hole properly, the sensor would turn on. If part of the sensor was covered, then the sensor would turn off, indicating a short or a long feed. We're basically using a photoelectric to do the same thing here with holes in the actual stock that's going through. The light grids here are being used. The BGL light grids are here to sense parts exiting the die. So they are emitter and a receiver pair. They are very similar to a light curtain, but these are for non-safety applications. They would have multiple beams at 5 or 7 millimeter spacing that would pick out a part as the part's being ejected. One of the challenges you always have in part out applications is the shape of the part and how the part falls out of the press or is ejected out of the press. Sometimes you may use a through beam sensor and the part may go under or over the sensor and not be seen. So the BGL light grid helps to solve that problem with multiple beams. So anywhere the part falls, we're bound to catch it with at least one beam and we know that the part has been ejected. Here's a buckle detection application using a through beam photoelectric sensor. So what we're looking for here is if the feed strip buckles at all, the sensor would break the beam because the sensor would be positioned a little bit higher than the strip, so it would pick up the buckle, break the beam, and stop the press. Here's another dual inductive / optical sensor system used for part out. So there's a prox you can see highlighted in red, and there's also an optical window. So the inductive prox sensor verifies that the air cylinder has returned because the plunger is being driven back. So the plunger moves into the tool to eject the stamped part, and then the window verifies that the part was actually ejected. Now this window is protected by steel plates on either side, and there's an optical cover that is inserted inside the window to protect the optics from contamination, grease, die cutting fluid, etc. Here's another sensor that is used for web or edge or strip control using the Balluff BGL analog fork sensor. So what this sensor would do is, if you can see it, it looks like a C-clamp. It's positioned with the strip inside it. It will actually tell you the position of the strip relative to the sensor, and you can measure a resolution of 0.08 millimeters. So as the strip moves from side to side, you're able to clearly tell where the strip is, and if you had this hooked into your control system, you can adjust the strip using a motor to make sure that the strip is centered back exactly where you want it. Specialty pressure and ultrasonic sensors. Pressure sensors are often used inside the die to detect the presence of nitrogen gas. So what you'll have in a press is you'll have nitrogen cushioning springs. If the pressure drops below a certain point, you want to have the pressure sensor set to signal so that the press will stop. And you also have air ports for blow-offs. So you want to measure the air pressure to make sure that you have enough pressure to blow a part off the die so that you don't cause a die crash. Ultrasonic sensors use sound waves to detect the presence of a part. In a press application, they'd be commonly used for loop control or roll diameter, so you're actually measuring the diameter of the stock entering the press. So you have a piece of steel that is going into a press, it's coming off of a coil, and with the ultrasonic sensor, you're measuring the coil diameter to check and make sure you're not going to run out of material feeding your press. Position sensors. Here is a linear transducer on a press. Common application for this would be shut height positioning. So what the transducer is doing is used to monitor the performance of the emergency braking system on the press. So it's going to measure the amount of movement or travel, and if an e-stop condition occurs in the press, the transducer would measure the amount of travel and aid in shutting down the press by making sure that the ram doesn't come down too quickly. Excessive travel indicates a need for maintenance or repair. So if you're getting excessive travel every time there's an e-stop condition, then somebody's going to have to go up and service the equipment. Ballast power remote systems, inductive couplers, send power and signals through an air gap to energize sensors and obtain sensor signals. So this is a wireless connectivity. No umbilical or unstamping presses are necessary. So non-contact couplers and networks. These are used for quick die change. You can remove the connector headaches and integrate RFID easily into the block. So what you see here is an example. The bottom left, the two heads of the inductive coupler line up. When the heads line up, power is passed from first head to the second head, which powers up your sensors on the die. And the block on the right shows the sensors on the die just connected to the die. So once they line up, then you receive power and you're able to power and monitor all the sensors on the die remotely without having a cable or a connector. This is a valuable tool when you're changing dies frequently. What happens a lot of times is during die changes, if they're using a hardwired connector, sometimes they forget to unplug the connector when they're making a die change, and then the cabling gets ripped off and the die has to go back to the press shop for rework to be rewired before it can be used again. So it can cause costly downtimes in the cable breakage. So there's a continued example on the right. You can see the press, you can see the Harding connector on the press at the right before, then you can see the Balluff block is the after. So there is actually no physical connection between two sides. Power is passed along the air gap and there's no need for the Harding connector. We're going to talk also about traceability in this portion. Traceability and tracking assets. So here we have a picture of a mold or a die, and we're using an RFID tag on that device and a handheld device to actually scan the RFID tag and tell what number we have on the part or the mold or the die. So for die tracking, What we're trying to eliminate is handwritten tags or paint shots on a die or numbers stenciled onto a die that the operator would have to visually identify. Instead, we're going to use an RFID tag on the die, and we're going to have a reader embedded in the press so that when the die is loaded, we simply read the RFID data carrier, and then we're able to identify which die is in place. We can also program into our die or into our press the setup conditions that that particular die would require, and they can all be done automatically rather than having the operator manually punch in information where mistakes can be made. So this is an area that helps reduce errors and make sure that we have the right die loaded in the press before we begin stamping parts.